Hey guys, in the last lecture what we had seen was to define properly the notion of stability and relate it to the transfer function, or how does transfer function have, or does transfer function have any information on the stability. And we characterize by saying that if all my poles are strictly on the left half of the S plane, then my systems are stable, right. And then we also had some special characterizations when there are repeated complex conjugate roots, how the system goes to an unstable behavior, and even when you just have a single pair of complex conjugate poles where the system was defined to be marginally stable, right. And all this involved computing roots of some higher order polynomial, could be 6, 7, 8 depending on how many poles there exist in the system. So, today we will try to find an algebraic way to see if there are better or maybe more efficient tests of finding out stability of the system. We may not be directly interested in the exact location of the poles, but an answer to whether the system is stable or not would be enough for the initial analysis purpose. So, what we will do today is to just look at a polynomial of a fairly higher order for which we cannot just compute roots by hand. What are the methods which evolved historically over time. So, this method is typically referred to as the Routh Hurwitz criterion. Okay, so we are again interested in the transfer function analysis, where I have on the numerator of polynomial of m and n, and then n is usually typically greater than or equal to m, right. And then the characteristic equation, which is essentially what happens in the denominator, when that is equated to 0, this is referred to as the characteristic equation of the system, no matter if your system is open loop, if you are doing an open loop analysis or even a closed loop analysis. We will formalize this characteristic equation shortly, but at the moment we are just interested in the denominator of a given transfer function for which we are interested to perform the stability analysis. Okay. So, the definition of stability leads us to a test which says, or which poses a question, are there any roots of the system on the right half plane? If the answer is yes, then my system is unstable. Okay, so let us do some steps here. So Q of S is a polynomial here, which I could write it in this way as a product of, so this will have some roots, let me call those roots as P1 to Pn, and these roots are the poles of my system. Okay, so if I expand this expression in terms of the poles, the expression would look something like this, right, again in decreasing powers of n until decreasing powers of s until you reach n equal to 0, right. Just to simplify this, so what happens when there are 3 poles, right, when this expression q of s, let us even assume that A3 would be equal to 1, then I have S minus P1, S minus P2, S minus P3, and this would expand to the following. You have S cube and S square. So, you will have sum of all the roots, it is what it says is P1 plus P2 plus P3 plus a term in S which is like P1, P2, P2, P3, P3, P1 minus the product of all these things, like here n equal to 3. So, I will have a minus P1, P2, P3 is 0. Okay. So, stability says that all the poles should be on the left half plane. So, let us assume or just say that so P1, P2, P3 are less than 0. Let us just for simplicity assume they are real, even though if they are complex nothing much would change also. So, if P1, P2, P3 are less than 0, then this entire number would also be negative and the coefficient of S square then needs to be positive, right. So, here similarly, if P1 and P2 both are negative, P2, P3 are negative, P3, P1 is negative, all these would, the products would be positive numbers. Similarly, if P1 is negative, P2 is negative, P3 is negative, that product would be a negative number and this minus would make it positive. So, what does the first observation say, right? If I have a polynomial like this and if I want to observe or if I want to say something about the location of poles in the stable region, the coefficients of this should be non-negative, right. So, that is one of the necessary conditions. It may or may not be sufficient, that we will see a little later, right. And all the coefficients, they should, well, they should have the same sign. Possibly there could be a minus, 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 minus all the time. That could, that's also allowed, because you just equate to 0 and then all the minuses would become pluses. Okay. So, the first observation, just by an expansion like this and keeping in mind that stability would mean the poles are on the left half plane, would lead us to say, well, the necessary condition is that all the coefficients are non-negative, right. It could be a 0, but if in this thing, if this is true, all the coefficients would be positive, right. Okay. So, this follow just from the general conditions of this polynomial. This is a general expansion when you have it of a degree n. Okay. So, some straightforward computation here would show that this ratio of or like the sum of poles from P1 to Pn could be expressed as a ratio of An minus 1 and An, and similarly the products and all. So, based on again these observations here, we could also say that all the ratios should be non-negative and of the same sign for the system to be stable. I am just rewriting those conditions in terms of polynomials. I am just dividing throughout by An, and since our An we assume to be 1 for simplicity, I think this would be very straightforward to find out. Okay. But these are not sufficient conditions, these are necessary, right. For example, I take a system which follows this rule over here, right, the s cube plus s square plus 2s plus 8 equal to 0. Well, this satisfies all these conditions that the coefficients are all positive, right. And now, does that guarantee stability? We will just compute the roots, and the roots turn out to be minus 2. Okay, this is a stable guy, and you have 0.5 plus minus j. Now, this guy, right, this guy sits in the right half plane. Okay. So, therefore, the system is unstable even though all the coefficients are positive, right. So, this the test that these things, all the coefficients are non-negative, is just a necessary condition. It will not guarantee things, right. However, if instead of a plus here, I have a condition like say s square, s cube minus s square plus 2s plus 8 equal to 0, it violates the condition that all these guys should be non-negative. So, this is definitely unstable, right. This is because I am violating the necessary condition. Okay. And then to have the roots computed, or at least to check where the roots lie in the complex plane, Routh and Hurwitz, I will tell you a story of this a little later, they came up with a condition which was both necessary and sufficient for the stability of linear time invariant systems, right. Okay. So, how does this go? We will not do the proof of it, but we will just learn the technique, right. So, the method has two steps. First is I just generate something called a Routh array and interpret the array in terms of locations of poles in the S plane. Okay. So, okay, we will read this statement once we see how the array goes. Okay. So, I have this characteristic equation, and I just write it into an array. I start with s power n. Okay, I take the coefficient here, I put a power n, and then I take s minus 1, I take this coefficient, put it here, and then I do all the coefficients of n, n minus 2, n minus 4 and so on until here, and then n minus 1, n minus 3 until I reach the end of the polynomial here. Okay, so these two are given to me. How about the remaining rows? So, given Sn, Sn minus 1, Sn minus 2, so this number is Bn minus 1 computed in the following way, that I take An minus 1 times An minus 2 minus of this guy divided by An minus 1, and just a simple formula. Similarly, I compute Bn minus 2, as again I start with An minus 1, I go to the next row here, An minus 4, again An minus 5 divided by this guy, right. So, this is, I think you could just look at this as a matrix and see the numerator is just the negative of the determinant of that matrix, right, and I just divided by this coefficient here, right, and I keep on doing this doing this recursively. Then I can have how do I compute the third thing, Cn minus 1? I start from here, I take Bn minus 1, I go to this guy An minus 3, subtract the product of with the product of An minus 1, Bn minus 2 and divide by this guy. Similarly, I do for Cn minus 2, I go from here till here, subtract this guy and divide again by Bn minus 1 and so on. Okay. So, I do all these steps, and what does this last statement tell me? The last statement tells me that the Routh-Hurwitz criterion states that the number of roots of the characteristic equation with positive real parts is equal to the number of sign changes in the first column of the Routh array. Okay. So, I have, so this thing here is the first column of the Routh array. So, An minus 1 to go to Bn minus 1 and Cn minus 1. If there is a sign change in any of these numbers, so by construction An and An minus 1 would be of the same sign, or they would, right, they typically both could be positive, right. So, if Bn minus 1 becomes negative, right, then there is a sign change, and we will see that with the help of an example. And then, and if this is a plus, say for example, and this is a plus, this is a minus, and this again becomes a plus. So, you see, well, there is no sign change here, there is one sign change and two sign changes. So, this sign changes will tell you that there are, or they will tell you how many poles are there on the right half plane. Right. So, that is what, again we will read the statement again, that the number of roots of the characteristic equation with positive real parts is equal to the number of sign changes in the first column. It will not tell you the exact locations, but it will tell you a first test, is my system stable or not, or all the roots of the characteristic equation, are they on the left half plane or not, or if they are on the right half plane, how many are on the right half plane, right. And so on. You can just keep on computing this array until you reach s power 0, and this is you just look at this column and check if there are any sign changes. If there are no sign changes, then my system is stable. If there are sign changes, then there are roots on the characteristic roots of the characteristic equation on the right half plane. How many are there? That will depend again on the number of sign changes. Okay. So, just to repeat, so for the system to be stable, it is sufficient that all elements of the first column are positive. Again, this I will just see why it is just a sufficient condition. If this condition is not met, in the way if there is a sign change, then the number of roots with positive real part is equal to the number of sign changes. So, if you just look at it this way, I go from An to An minus 1, I ask my question, is there a sign change? I go from An minus 1, Bs minus 1, and I keep on asking this question, is there a sign change, is there a sign change, right. And when the answer is no, then I can conclude that the system is unstable. And if there are sign changes, if the answer is yes, even once, then the system is unstable. And the number of times I change the sign, that equals the number of roots on the right half plane. Okay. So, just as an example, right. So, I start with a fairly simple looking polynomial, s cube, 4s square, 9s and 10, everybody is of the same sign. So, the necessary condition is met, right. So, let me go about drawing the Routh table. So, I start with s cube, which is the highest order of the polynomial. So, I have 1 and 1, then I go to s square, there is a 4 here, then s n minus 1 would be, I am looking at s power 1, that is 9 here, and then I plug in a 10 here. And then I just compute, how do I do this? So, 4 times 9 minus 1 times 10 divided by 4. So, I get a number here 26 times 4 and then a 10 here, just by looking at the formulas for Bn minus 1, Cn minus 1 in the previous slide. Okay. So, what question do I ask? I just look at this column and I ask, is there a sign change from 1 to 4? Answer is no. From 4 to 26 by 4, again the answer is no. 26 by 4 to 10, again the answer is no. So, all there is no sign change, no sign change, no sign change, and therefore, the system is stable, right. Okay. Now, in the case of an unstable thing, right. So, you have s cube and s square, 3s and minus 5. Okay. So, this again by inspection is unstable. Okay, now let us just verify what the Routh guide tells you. Okay, so I just do s cube is 1 and 3, then s square I have 1 and minus 5, then I do all the thing and I just find a sign change here, right, from 8 to minus 5, and therefore the system is unstable. You could even compute the roots exactly and say that, okay, so you have 1, this is the unstable guy, and then okay, these are two stable poles. There is one sign change, so one pole on the right half plane, right. This is what this last statement tells you. Okay. Now, let us do some other example. So, I have S5 plus S4, 2s cube plus 2x square, 3s plus 15 is 0, and my necessary condition here is met, right. So, again I start constructing the Routh array. So, S5 is 1, S cube is 2, S power 1 is 3, and S4 is 1, S square is 2, and S power 0 is 15. Okay. So, something strange happens here, right. If I look at this matrix, well, the determinant is 0. So, something strange happens here, and these are like the special cases, right, where there is a 0 in the first column. Okay, what do? Do I just leave it here and say, well, there is no answer to this problem? No, there is a way out of this, right. If the first element of any row is 0, then just replace this by a small positive number and call it epsilon, okay. And this epsilon value epsilon is allowed to approach 0, it is like very small number, and then we compute the Routh table now with this epsilon being a small positive number, and then interpret the table for the stability. Okay, how do we do this? Okay, so the way we compute is, instead of the 0 I substitute an epsilon which is considered to be greater than 0. Then this element is computed as twice epsilon plus 12 over epsilon, and I have a 15 here, and then the s power 1 term turns out to be this, again doing this computations. And okay, now closely look at this term, right. As epsilon becomes very small, we could even take the limit as epsilon goes to 0, this guy becomes a negative number, right. I just have 144 by 12. Okay. So, this, and then the last number becomes 15. So, I just keep traversing here, I say, well, there is no sign change from 1 to 1, no sign change from 1 to epsilon, as epsilon is assumed to be positive. Since epsilon is assumed to be positive, this is also a positive number. Then I go here, this guy becomes negative, and again the last guy is positive. So, I see there is a sign change and there is another sign change, right. So, since there is one negative element here, the system is definitely unstable. And then how many sign changes are there? This is a plus to minus, one sign change, and another again a minus to plus, right. So, the system is unstable. Further, this table or this row tells me that there are two poles of the system in the right half plane corresponding to two sign changes. Okay. So, well, let us see another case. So, I have s cube, 5s square, 6s and 30, and then I put this in the table, I plug these numbers in 1, 5, 6 and 30. Okay, so there is something strange happening here, right. So, the entire row is now going to 0, right. Okay, what do I do now? Do I really substitute epsilon and epsilon again and do the analysis? Well, the answer is no, because you will still again encounter a 0 if you do that, right. Okay, so what do we do here? We be a little more careful that if an entire row is 0, we form something called an auxiliary polynomial with the row immediately above this guy, right. So, this is S1, and I form a polynomial with this guy S square, which has entries 5 and 30. Okay. And what I do is then this polynomial is differentiated with S, okay, and I will have then a, so if this is a polynomial of order 2, then I will have something in order 1 here, right. The rows of this guy is then replaced with the coefficients of this differentiated term, of this differentiated auxiliary polynomial with respect to S. Okay, let us see how this works. So, I have a 0 here, the polynomial just above this is 5s square plus 30, I differentiate with S, and I get this is 10s plus 0. I take this 10, I plug in here, I take this 0 and I plug in here. Okay. So, that will, so my new table would now look there like this, right, then Routh array. So, I differentiate, I take 10 and 0 and then I proceed with the rest of the computations. So, this guy will just be 30 and then I again do the sign change test. Is there a sign change? The answer is no, 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 and therefore, I can conclude that the system is stable because all elements of the first column are positive, right. Okay. There is something little more here, right, that since this guy is entire row is going to 0, there is an existence of a pair of roots which are on the imaginary axis, and that is simply given by solutions of this equation. 5s square plus 30 equal to 0, you solve this, this will give you the exact location of the roots on the imaginary axis. So, whenever an entire row goes to 0, then you detect a pair of roots on the imaginary axis, okay, or this actually the conjugate pair. Okay. So, what if there are more of these auxiliary polynomials, right? So, the auxiliary polynomial is essentially it has the highest power is of course an even number, like so it could have S4, S square and so on, or maybe say S6 or S8. So, this is its highest power, right. And then you could have all the other powers could be here S square, S power 0, S power 4, S power 2 and so on, right. So, it will be all just have even powers S6, S4 and so on, right. Okay. In this case there are, what we see is there are roots that are symmetric about the origin, and symmetry could occur under several conditions, right. Symmetry could be like here, right. So, from you have a -1, you could have a +1 here, they could be symmetric just and lie just on the imaginary axis plus j omega and minus j omega. There could be something like this also, right. You have +1 plus j omega, -1 minus j omega, you have this is a -1 plus j omega, there is a symmetry from here till here. So, this will, if this is a -1, this will become a +1, and if this is +1 plus j omega, this will be minus, so it is +1 minus j omega, and here this is symmetry about this imaginary axis. So, if this is a +1, the real part will become -1 and so on, right. And the roots of the auxiliary equation are also the roots of the characteristic equation. Okay, this again appear only when these kind of things happen. Okay, so let us do another polynomial here, right. I have S5 plus 2S4 plus 2S cube, 4S square, S2 all being equal to 0. Okay, so I construct my Routh table and I take S5, so I have a 1, then S3, the 2 goes here, 1 goes here. For S4, 2 sits in here, 4 goes here and this goes here. Okay. So, so whenever you have things like this, you could just even replace, just divide this by its common factor, right. So, this could even be 1, 2 and 1, right. So, you can divide by 2, divide by 2, divide by 2, it will still be the same analysis, right. And you see that the rows are the same, right, and therefore, this entire row of S cube goes to 0, right. Okay, what do I do now? I first construct the auxiliary polynomial, that is in S4. So, you have S4 plus 2S square plus 1 equal to 0, right. So, it will be the same even if you write 2S4 plus 4S square plus 2 equal to 0. I just take the 2 factor out and then I differentiate, dA by ds would give me 4S cube plus 4S plus 0. Okay. Now, I go here, right, I just substitute this entries 4 and 4 over here. Right. So, this would be 4, 4, and since 4 is common, I just get rid of the 4 and I can just write equivalently a 1 and a 1. Okay. Now, I compute S square and what I get is again a 1 and a 1, and not surprisingly because this is 1 1, this is also 1 1, there is another 0 entry here. Okay. Now, I construct further one more auxiliary polynomial. So, I keep on doing that each time I encounter a row which has entries which are completely 0, and then I take this guy, the second polynomial I call it as A prime, and s square plus 1 equal to 0, I differentiate, I get 2 and then I get an s here. Okay. So, I just do this. Okay. Now, there are no sign changes. So, can I say, well, this system is stable? Well, from my stability theory, we had learned something, right, that if, okay, let us just draw the complex plane here, I have a sigma, j, omega, everything here is stable. Okay. So, if I have a root where this is plus j, minus j, this I called as marginally stable. If I had something like this, say plus 2j minus 2j, this was also stable marginally, even though marginally. But if I had repeated roots like this, plus j, minus j, then there was, we derived that these roots actually lead the system to instability. Okay. Now, where are these? So, I know that there are now 4 roots on the imaginary axis, right, 2 coming from because of this row and 2 more coming because of this row. Okay. So, let me calculate the roots. So, s square minus 1 equal to 0 would give me roots as plus minus j, and then I even further here, if I calculate the roots, that will just give me another plus minus j, right. So, I have 4 roots which are plus j, minus j and minus j, and these are repeated roots on the imaginary axis. And we concluded in the stability analysis class that when I have repeated roots on the imaginary axis, then the system goes to being unstable, and therefore, we conclude that this system is unstable. Okay. So, these are the special cases which we need to be careful of while we are computing stability, right. So, we just need to remember all those cases which we analyzed during the stability class. Okay. A bit of history here. So, where did all this start from? So, this had roots. The Routh-Hurwitz stability criterion was developed somewhere in the 19th century when Maxwell, the famous guy of the Maxwell's equations, they became interested in stability of dynamical systems, right. And this Maxwell was motivated by this analysis of centrifugal governors, which was essentially invented by James Watt, right, for his steam engine, right. Okay. So, Maxwell was the first to make some initial guesses around this thing. He was the first to provide a theoretical analysis of feedback systems using some linear system, right. So, linear differential equations. Okay. So, this was how the governor looked like, and this is a picture which we got from Wikipedia. So, what did Maxwell say in his paper? So, this is from his paper in 1868 called On Governors, which appeared in the proceedings of the Royal Society. You can still download it. So, what Maxwell said, that the condition for stability of the governor, so this guy here, is mathematically equivalent to condition that all the possible roots, they still did not define this because they did not have a notion of right half plane, left half plane, stable roots, unstable roots, marginally stable roots and so on. That all the possible roots. So, he said that the stability was equivalent to condition that all the possible roots and all the possible parts of the impossible roots of a certain equation shall be negative, right. So, this is a little misleading because they did not have any formal terminology to define it. So, essentially he meant that all roots must be negative, right. So, possible roots were all the real roots, they shall be negative, and then you could have impossible roots which were imaginary, and you say the possible parts of the imaginary roots were the real parts, right. And these possible parts of the imaginary roots, so of the impossible roots, for an example, minus 1 plus j omega was regarded as an impossible root, but this was the possible part. All this should be negative, right. And then Maxwell could do it for a third order equation, right. So he said that I have not been able to completely determine these conditions for equations of some higher degree than 3. And then he posed this problem to a set of mathematicians, right. And then, so this analysis by Maxwell led to the subject for the Adams Prize in 1877, with Maxwell was being as one of the examiners. And then the problem which was thrown at mathematicians was to find a general criterion for dynamic stability of systems, right. And then later on Edward Routh in his essay called A Treatise on the Stability of a Given State of Motion, presented this condition which we learned just now from the Routh table. Okay. So, parallelly and not surprisingly from Russia, there were also people working in similar areas, right. And then the results again of a steam engine with a governor, these were used by some guys to design water turbine governors. And then Stodola with his collaborator at ETH in Switzerland independently also arrived at the stability criterion, and these two actually evolved independently, right, using some different methods, right. And to honor this parallelly evolved result, so the stability criterion is now what we know as the Routh-Hurwitz stability criterion. And this is a little interesting story of how this stability criterion evolved. Okay. So, what we, and these are the papers which you could actually refer to, right, to see the history of all this analysis of stability of differential equations. Okay. So, what we learned so far is the Routh-Hurwitz criterion, some special cases of what happens when there is a 0 in one of the entry, what happens if there is a 0 in the entire row, then we did the analysis of the auxiliary equation, right. So, next week we will look at more. So, at the moment we just looked this analysis only in terms of roots of a certain polynomial, right. So, next time we will give it a little more control flavor, analyze this in terms of feedback, then we will do things related to sensitivity. We will also slightly introduce the concept of relative stability, what relative stability means, and we will see if we could solve some of those relative stability criterion or relative stability problems using Routh-Hurwitz criterion. Thank you.